All right, everybody, let's get started. Good afternoon, folks. Welcome to the Lunchtime Discovery Series. It's good to be with you again for another edition of our program, brought to you by the North Carolina Office of Environmental Quality and broadcast and hosted by us here at the North Carolina Museum of Natural Sciences. Most Wednesdays, gathering right here at the museum's YouTube channel at noon to bring you interesting people doing interesting things out there in the worlds of science and the environment and education. We have every single week. So make sure that you bookmark this program, sign up for the email newsletter. You don't want to miss the Lunchtime Discovery Series. It's a long-running program. We have an incredible art, and we have a great time engaging with our guests every single week. So it's good that you are all here today. I hope that I continue to see all of you hanging out with us here on the YouTube and in the chat throughout today's program and in the future. Say something like, we meet interesting people doing interesting things, and they teach us a little bit about what's happening in North Carolina and even sometimes around the world. Today, our purview for the Lunchtime Discovery, we're going universal with it. We're headed out to the far reaches of space just so that we can turn around and take a look back at what is happening here on Earth and even here in North Carolina. Because today's natural sciences and is an Appalachian State University. Hi, Rachel.
Hi, Chris. This was great. Thanks for. Yeah,
we're both excited.
We're both.
A lot of the presentations that you've been doing, some community groups I've seen, you bring this awesome software in order to.
Yeah, it's yeah. Tool that we've been using for the past 7 years now in partnership with the American Museum of Natural History. It's a NASA-funded project to develop this software to basically take people from Earth to the edge of the universe. And there are many data sets involved, and it's a wonderful tool for education, for outreach. And I really love, I've been talking about astrobiology and the search for life beyond Earth for a while. And now with OpenSpace, it becomes a much more dynamic presentation. So I'm excited to share this content. Oops, did I lose you? Oh, you're here. Sorry. I clicked something on my thing. All right, there you go. So with OpenSpace, we'll fly from Earth to the edge of the universe and hopefully actually bring in context to North Carolina, because we are on planet Earth. And there's a lot of relevance locally and thinking about the environment and especially our habitable planet and in the context of what's out there in space. So maybe we'll have a broader context of our own world after hearing about some other places that aren't so friendly as far as survival goes in space today. So
Rachel, if you want to get your presentation going.
Yep. All right.
I'm going to remind all of the viewers to put questions in the chat or in the comments as we go through the program. We're going to be taking your thoughts and questions at the end. Also, later in the program, I'm going to be sharing a link to a survey for the folks at OpenSpace about today's presentation. So be on the lookout for that after the show in order to submit your feedback.
Yeah, and thanks for mentioning that, Chris. So everyone who's watching, if you fill out this survey, it's very helpful for the project, for the team in New York to get evaluations for our presentations. And we don't actually see them personally, but the team sees them, and it's really helpful to know the kind of impact we're having with OpenSpace in various ways. So I'll get started. How does this look, Chris? Is everything moving all right? And you see the screen, I hope?
Great. I think your Zoom is over part of the screen at the bottom.
Oh, it's still a part of the screen at the bottom. All right, let's try to hide that again. Hide meeting. There we go. How about that? Is that better?
Now it's in the middle.
It should go away.
Okay.
All right. Now we're going?
Looks great.
Good. All right. So welcome to the solar system, everybody. I'm just going to show a quick context of where the Earth fits in the galaxy and in the universe, in case this, and this maybe review for a lot of you, but it kind of puts in perspective where we are. And we, of course, are on planet Earth. And this little blue line here is the orbit of our planet around our star, the sun. And I'm going to zoom out. You might see some other blobs here. This is a moon system of a giant planet. And I'm going to zoom out a little bit just to show kind of, this the orbital plane of our solar system. So we're going to talk about our planet. We're going to talk about some planets in the solar system, and we're going to talk a little bit about exoplanets today. Hopefully we'll get to all of that. So this is our little disk. It's a remnant. This shape, this dinner plate shape, this flat shape is a remnant of our disk when we formed 4.6 billion years ago. And so we're going to zoom out. And as we zoom out, I'm going to just turn on a data set here, and this software you can actually download yourself, and it's called OpenSpaceProject.com, and I'm just looking here for let's see, where am I? Sorry, so there are a lot of data sets, as you can see, and I am looking for other. And so what I'm going to turn on now, we're going to come back to this, because we are talking about the search for life. This grid that I just turned on is called the radiosphere. And this is the extent to which we have sent signals in terms of radio waves and television and light from our planet. And it extends only 100 light years in each direction, roughly. And that means if we're at the center of this sphere, it's 100 light years this way and 100 light years this way. And that means it takes 100 years for light to travel to the edge of the sphere in each direction. And that is basically the farthest we've sent any signals out to space. And to give you perspective of how far that really is, I'm still zooming out. We're in our galaxy still, and follow that little dot. And here's our galaxy. We are one of a few hundred billion galaxies, right, in our universe. And our star is one of about 400 billion, roughly 300 to 400 billion stars in our galaxy alone. And this is our little radiosphere right here. So this is as far as we've sent signals. Now we can look very far with astronomy, with telescopes. You've heard of probably James Webb Space Telescope, launched recently in December. And we have all this great data coming, and I'll share a little bit of that with you today, some of the latest stuff we have. But this is the extent we've sent signals. So if there's life out there, if perhaps there's a civilization out in this direction, what we have not reached them yet. A signal from us has not reached them yet. And similarly, a signal from them would not have reached us yet. And so we have a long way to go before we can actually explore the full extent of our galaxy and our universe as far as making our presence known. And that's important to remember, is that we still don't have evidence for life beyond our planet. And we'll talk today about how we search for life. These are galaxies and galaxy clusters that we're now pulling back into. This is all data, real data from missions and telescopes. And this is a blind spot we have. So we can't see everything. Similar, like you drive a car, you can't see everywhere around you. You're supposed to turn your head when you make a turn, hopefully, or pass. But this is a blind spot, so we can't see everything. But we know that most of everything should be filled with galaxies. And then finally, and I'm pulling back here, billions of light years. This is the cosmic microwave background. So this right now is an image made from the heat left over from the Big Bang, which created the universe. And that was 13.77 billion years ago. So the light that left, the heat and light that left the Big Bang took 13.77 billion years to reach us. So this is the farthest we can see in our universe. Now, we don't know what's beyond that. We don't even know if there's anything, the universe could be much larger than our observable universe, but we're just learning. And so what James Webb Space Telescope will do is peer back in time to about 100 million years from the Big Bang and look at the earliest galaxies, the galaxies that just started to form about 100 million years after the Big Bang. And that might help us understand better what dark matter and dark energy are that hold the universe together, and also help it expand and accelerate. And so we don't know and really a lot about dark energy or dark matter, but James Webb Space Telescope, by looking as far back in time as we can get, will help hopefully open up some windows into that, into the mysteries of dark energy, which is most of what the universe is made of, dark energy and dark matter. All the matter that we understand, everything from planets to stars to everything we have on planet Earth, is regular matter, and that is a very small percentage of what the matter is in the universe. It's less than 5% of the mass of the universe is actual matter that we understand. So let's zoom back. Hopefully have a little perspective. Here's our galaxy again. And we're going to go back to Earth. And when you download, if you want to download OpenSpace, you can take some tutorials on the website to learn how to drive. And I'm going to turn off the radiosphere because it does get in our way. And what I'm going to turn on while we're here is solar system, small bodies. I'm going to turn on some of the asteroids because these are the leftovers from our solar system forming. So remember I said that the universe formed 13.77 billion years ago. We're very young. Our solar system, relatively speaking, formed less than 5 billion years ago. So our search for life is really potentially looking for much more advanced life than ours. And I'm turning on the asteroids, which you can't see yet. I'm just turning on a couple of them. Let's see, Jupiter's, these are some good ones. And we'll zoom back in. It does slow down a little bit. So because these data sets with the asteroids is thousands of thousands and thousands of asteroids in this data set. So what you'll see here is some of the asteroids in our solar system. And we know asteroids, we get remnants of asteroids as meteorites. And I'm also curator of the meteorite collection here, and I'll show you some images that I've taken from some CT scans of meteorites, trying to look at the insides of them, of some really nice meteorites we have in our collection, trying to study the early solar system. So a lot of the work I do with forming stars connects to our early solar system, and the material we have to work with from our early solar system are asteroids, comets, and the meteorites. And you may have heard some recent news of missions that are returning samples from asteroids. So pristine material from asteroids are coming, some have come to Earth already through the Japanese space program. And the asteroid is coming back in a couple of years from Bennu as part of a NASA program to really start studying these pristine samples from the asteroid belt. And before I turn on kind of a picture of our protoplanetary disk, what I want to emphasize too is that here's some images. This is an image, you may have seen this from James Webb. This came out a few weeks ago, roughly. This is the Carina Nebula. And this is just to emphasize, this is a beautiful infrared image. It's colorized to show different wavelengths. So James Webb Space Telescope observes at a wavelength we can't see with our eyes. So it's not optical like we see. So it has to be shifted in the spectrum for us to see it. And what astronomers do is they assign colors to those wavelengths. So the red colors are farther away and they're more dusty, and the blue colors are closer typically. And what you see here though is this beautiful landscape of basically this molecular cloud that's forming stars. And all of these beautiful stars, there's some stars that are in front of the cloud, but many of these dots are inside the cloud, and they are forming stars today. They're forming systems today. And so there's probably billions of exoplanets that are going to form and are already out there for us to study. And we only have a very small handful of data still on what's out there. And we're really trying to, all the work I do, the work my colleagues do, and really the scope of a lot of the astrophysics and planetary science that you hear about is really trying to understand not only how planets form, but also how we form and where we fit in the universe and in the galaxy in terms of what makes a habitable world. And we still don't have data yet for any life beyond our planet, even if it looks like there should be life out there. There's tons of material and chemistry happening and all of these planets and all of these stars. It's hard to imagine that there isn't life out there. And yet we still don't have evidence, so we don't know. And I'll just move on to this next picture. This is a sketch of a protoplanetary disk. So we know these disks form. This is how our solar system formed as well. So this is a disk of gas and dust around a forming star, just like our sun was forming 4.5 roughly billion years ago. And from this material, we get planets. And most all stars are thought now to have at least one planet, and that's a lot of planets. So that's what makes it really exciting to see, you know, all the kind of data we can get from James Webb and from other telescopes to learn about exoplanets, learn about star formation and exoplanets forming today, because we think there's so many planets out there now, and that really opens up opportunity to potentially find life. So the remnants of this are the asteroids and comets, and this is back to our solar system again, some of the data. So you see here all these dots, the smaller dots. This is closer to our Earth, closer to Earth, and these are farther away. These are more comets, and they have much they are much farther out in the solar system, and they're more icy. And so we see comets when they come in close to the sun, and we see the beautiful tails. But most of the time, all of our meteorites, for the most part, are from asteroids, with the exception of a few from the moon and a few from Mars. And one thing is really cool is that these are the Trojan asteroids, these blobs of green dots. And what's cool is that this is Jupiter with its little moon system here, and Jupiter is so massive, it's more massive than all the planets combined, and almost became a star. It is so massive that it clears a path for these asteroids. So asteroids can't get any closer to Jupiter than this, and it also absorbs a lot of these asteroids so they don't hit us as much as they would have. And we think a planet like Jupiter is really important for life to evolve on Earth, because without Jupiter, we would be pelted with comets and asteroids much more often than we have been in the past, and also currently. So this is some of our asteroids, and there's plenty of asteroids that are around around Earth that are called potentially hazardous, and it's possible that they could hit us one day, but not in the near future. And so OpenSpace is really nice to visualize a lot of these asteroid data sets, and I'm only showing you a very small portion of these asteroids. There's a lot of them out there. They do slow the program down a little bit because there's so many. But I'm going to now go ahead and turn these off so we can look at something else. So speaking of asteroids and impacts, we're going to go to a place that I really like to show for astrobiology, and that is Meteor Crater. And some of you may have been there. I bookmark. You can bookmark things in OpenSpace, which is nice, so I can find it again without having to look for tiny little locations. It really puts in perspective how small everything is when you have the whole universe at your disposal, and then you're trying to find a little tiny crater on a planet. So I'm looking for Meteor Crater, which should be somewhere here. Oh, here it is. Perfect. So I got my little bubble. And now I'm gonna, whoops, I don't want that. All right. So now I'll get there for us. Hopefully it'll show up for us. Sometimes the internet can slow things down. This is our beautiful planet, right? I'll pause for a second. We do, as Chris mentioned, this series discusses the environment and our planet. This is our planet, and we have a very thin atmosphere, and this atmosphere keeps us habitable, keeps us alive. We are very special in terms, we think, at least for our solar system. There is no planet like ours. If there isn't even a location in our solar system as hospitable as anywhere on Earth, which means, for example, the top of Mount Everest is a balmy day compared to any place on Mars. And so we think maybe it's easy to just hop over to another planet and set up camp there, but it isn't at all. And there's a lot to consider when we're sending people to space. And the mission Artemis they were going to test this launch that's going to send humans to the moon again. And the test launch was actually scrubbed I think it was yesterday, because of something with the engine, but they'll get there eventually. And there might be something, I have to see that somehow this data set doesn't want to go. We should get to Meteor Crater soon. I don't know what's going on with Earth. Sometimes the data sets get a little, they pull from a server. So it's possible we may not reach this crater today. I will try one more thing. You can't, let me we won't linger too long. So this is not actual real time, but it is real. So Earth data is pretty recent. So it could be yesterday, it could even be this morning. A lot of the other data I'll show you has been already put into the program, like the data from Mars. So it has to be imported. While we wait for the crater, we can look here near the Grand Canyon. This is near Arizona. So unfortunately, Earth is not behaving or cooperating very well. But what I'll emphasize here, you know, we have water on this planet. A habitable world needs to have water on the surface. There is not any place in the solar system that has liquid water on the surface for any length of time. So we need to protect our planet, and that certainly is a daily thing to think about for everybody, no matter where you live, and climate change and how we're impacting this planet. And so as we think about space, just remember, this is our tiny little habitable home, and there is nowhere to go right now. And so this is a big question of humans in space in general, is when are we going to go? How are we going to get there? Who's going to go? All of these big questions have to be worked out. But in the meantime, we should think about protecting our own planet. Unfortunately, we're not going to get to this crater for some reason, but that's all right. What I'll show you instead is that we have meteorites. And so this is what I was going to show you anyway. This is a piece, an image from a CT scan of the Chelyabinsk meteorite. And the reason I'm showing it is because Chelyabinsk it came over Russia in the little town of Chelyabinsk in 2013, and is a reminder that we still get impacts on this planet. This atmosphere here protects us from a lot of impacts. They burn up as they come in, but not everything. And this was actually a fairly small asteroid, a piece of an asteroid. It was about 30 meters across, which isn't very big at all. But it was not expected. We weren't able to see it in advance because we don't have the technology set up yet or invested in to really monitor these anything less than, say, 150 kilometers across. So this chunk, and this is a tiny piece of the big meteor that came through, they weren't able to plan for it. And so it actually did a lot of damage to the town, and people got hit in the face with glass because they pressed their faces up to the glass. They saw light come through, and then the shock wave came after that, and the glass came in their faces, and nobody was fatally injured. But it was a reminder that as we populate this planet, we're still going to get visitors from space, and these rocks, while scientifically interesting, can do a lot of damage too. So we should think about perhaps planning for smaller bodies to observe them, to really understand how many there are. And since we can't get to the surface, I'll turn on something, the potentially hazardous asteroids. These lines here, I'll turn this off a second. These are all of the potentially hazardous asteroids. There are thousands of them, and they're very close to Earth. And they're called potentially hazardous because, what's going on here? Because I got a little frozen here. What's happening? Oh, it doesn't want to move. All right, it's just crunching along a little bit. They're called potentially hazardous because in the next 100 years, we could get an impact. But again, these are large bodies. We don't have the technology to see these smaller ones. And so when we think about how does that matter to us, well, yeah, you don't want to be hit by an asteroid. The chances are pretty low that you'll be hit by an asteroid. But also thinking about habitability, thinking about habitability is, I think OpenSpace froze a tiny bit. Hold on a second. I'm a little bit, darn it, what is happening? Sorry, everyone. Sometimes it gets, see, we can always come home. Purchasing, I found it has almost 100 amino acids in it. Some are extra. Like glycine is found in Earth, and acids is very I don't have a picture of, which also has amino acids. It fell over a little piece of it, and hopefully I'll get to working on it a little bit. Anyway, as far as this is a really interesting one. And thinking about for life or I had some images of a couple, but I will skip those. James Webb Space Telescope. James Webb Space Telescope out at 10 miles from Earth, getting us do is actually I use ground-based telescopes in Hawaii, and in October I'll be going back. We have time now again, so and back in person. And so this is Hawaii, so I have to turn on daylight. It's quite a bit earlier there. Oops. Come on. Okay. And so the reason ground-based telescopes can be an advantage over space telescopes is that the instruments can be larger. And so let's hope that we can get there. If we can't, that's okay. We'll go somewhere else. We can always fly anywhere we want with OpenSpace. We can go to the moon and Mars and beyond. So we have a lot we can talk about. I was going to bring in, I don't know what's going on with Earth today. It could just be a delay. We'll just hold on a second. But Mauna Kea, this is in Hawaii. This is on the big island of Hawaii. As soon as it loads, if it does, is probably the best location on Earth for observing because it's very high. It's 14,000 feet. And it has a lot of great weather days. And so there are about 13 observatories up there. And the one I use is NASA Infrared Telescope. It's the Infrared Telescope Facility, IRTF. And it's a small telescope. Right now I'm using this one. It's about 3 meters in diameter, the mirror. And I'll bring this in later when we talk about extraterrestrial intelligence, because the telescope was built to support the Voyager mission, which was launched in the 1970s and has on it these to image the giant planets. So this telescope has been around a really long time and has these golden records on it. So in the off chance extraterrestrials find it, Carl Sagan put on these records. So we'll talk a little bit about it. I think something's wrong with the Earth data today. I don't know why, so I'm sorry about that. Mars is definitely working, but it usually looks really nice. So I know that doesn't sound great to say it usually looks great, but I swear it does. But anyway, what I'll show you here, since I have my backup pictures, is that there is this beautiful plant up there called the Mauna Kea silver sword. And I actually, when I go to Mauna Kea, because I can go observe on the summit, I love to visit this plant. It's very robust. So I think about, it's quite advanced. And again, it's a balmy day on Mauna Kea, even in the snow and ice, compared to anywhere else in space. But it does have that kind of extraterrestrial look of Mauna Kea, this landscape. It's rocky, and you can easily see where life kind of stops growing up at about 9,000 feet. So this is about 9,000 feet. This is called the Mauna Kea silver sword. And it's a beautiful little plant. It flowers once and then it dies, which is kind of dramatic and sad. But they're having a really hard time. It's very endangered. They're having a hard time reintroducing it. It was munched on by livestock several decades ago, and they're trying to reintroduce it. And it has these really cool little hairs on its leaf, I guess those are leaves that hold in water, and it can survive really pretty extreme conditions. Now, again, this isn't that extreme compared to space, but it's one of these environments that's fairly unusual, where you can go and kind of imagine, or at least I do when I go, you can walk around out there on the mountain, is to imagine, could this be like, if humans ever get to Mars, maybe this could be the type of landscape we'd eventually get to if we were ever able to terraform Mars and change it to be more like Earth. And that may never happen, or it just may take a very long time, probably a long time. So anyway, this is the flowering stalk. So this silver sword, this part's going to die, but these little guys here are okay. So anyway, but this is the landscape. So it's very high, it's dry, it's above a lot of the clouds, but not all of them. And it's water vapor that you worry about for observing. So that's where James Webb and Hubble and all of these telescopes in space have this great advantage, is you have no atmosphere to deal with. But you do have smaller instruments, and they also can't be serviced. So Hubble could be fixed, Webb not. Webb is out in called Lagrangian 2. It's out 1 million miles away. It's too far for astronauts, at least for now. So the plan is not to service that telescope. And so it's kind of out there doing its thing. It's a beautiful, revolutionary piece of technology. It's still, for the work we do with gas around these disks, for the type of observations I'm doing, this is the telescope that really is useful, because it has a great instrument on it that is only really, there are only a few telescopes that have it. So this is the little dome up, this is at 14,000 feet. This is the, you can go inside and, you know, wear a jacket. It's very cold. Everyone thinks Hawaii doesn't get cold. It certainly does up here. This is how we observe. So across the wall of that dome, we have computers. We don't look through an eyepiece. We still observe with these big telescopes. We observe with computers, and there are at least one other person there helping to operate the telescope. So it's a pretty big operation with these large observatories on Mauna Kea. And we take some pictures. So this is a forming star. This is a massive star forming in our galaxy. So it's part of the work that we're doing. These are winds blowing off the star. So this type of object is really cool. We can learn a lot about the chemistry that's happening, because there's all this gas around it. So I'm looking at carbon monoxide and getting some really nice spectra. This is one spectrum I'll just show you. So this is the data, this is what the data look like. You can ignore the numbers and stuff, but the lines coming down are carbon monoxide lines. So it's CO. And these beautiful, straight, lovely lines are the data that I can then analyze and tell you how much of the gas is there, the temperature of the gas, and it gives a lot of information about what's happening around each of the forming stars that I look at. So how does that apply for life? Well, you know, this is the chemistry that's needed to be understood if we want to understand how planets form and eventually how life forms, because carbon monoxide, it has carbon. It's a very important molecule for chemistry. So that's the only spectrum I'm going to show you. Anyway, that's another planet. So that's all I was going to mention about the work I do. So that's the kind of it. I'm excited to go back in October. And now we're going to go to Mars. We're done with Earth. It didn't cooperate with its data sets today. I'm sure as soon as I'm done, I'll go back and it'll be like perfect. That's what happens. All right. So I marked Jezero. This is a crater I like to go to. It's Mars 2020. We landed there not a couple years ago, and I'm going to make it nice and bright for us. Now, what you see here on Mars is I'll just pause a second. Mars is our closest planetary neighbor that we're going to eventually go to. Most likely, it'll probably be 20 to 30 years, I'm thinking, and the consensus generally with reasonably minded scientists is that it's probably going to be a long time. The moon will go back probably within this decade. It's not that hard, honestly. We just need a rocket, and we've got a rocket, and it'll go. The Mars is much different. Mars is much farther away. We have to work on radiation to make sure the astronauts survive the trip, which takes about 8 months or so. And then what are they going to do when they get there? They have to survive living there for a while, at least 2 years, really, in order to get back. And so that's a big deal. And then just getting there, and then this planet has no atmosphere, has a very thin atmosphere. It has some atmosphere, but it doesn't have support liquid water on its surface. However, it did in the past. And Mars probably had a global ocean, in its northern hemisphere. We think it had an ocean, and it certainly had flowing water in the past. And so when you hear water, that means possible life. And so that's why we keep going to Mars, to look for that life, look for fossil evidence for life, and look for just understanding what happened to this planet. And Jezero crater, which is here, and it was working, so we will have good thoughts here. Here it is. It's one of these little tiny craters that I'm going to turn this thing off. All right. So Jezero is, and I gave up on Earth. I was going to show you this analog, this place in Turkey, this lake. It's called Lake Salda, And it was studied. It has these minerals around it that are very similar to the mineralogy that's around this crater. So this is actually an ancient river delta, and you can see that. You can see the ancient channel here. This is a river channel, and all of these squares, by the way, this is all real data that came from Mars Reconnaissance Orbiter that's been orbiting Mars for several years, for few decades now, almost 20 years. And so this is all actual data, and that's another thing to emphasize with OpenSpace. This is not animation. This is all rendering from data sets. And that's what makes it such a really nice, authentic tool, which I love for teaching and for showing people, because you're looking at actual data and really cool ways to visualize it. And you can go, everything is a straight, you have all your data there, all the stars are in the right place. And so everything is a really nice journey you can take to so many different locations. So Mars 2020 landed right about here. And Jezero is a really cool place because of this ancient riverbed and this delta here that is where basically, like the Mississippi Delta, water came flowing through. And all of these, and there's so much mineralogy here that could have been from possible life. Now, there's no evidence for the life yet. I'm going to try to get down closer to show you. There's no evidence for this life, so keep that in mind. No matter how much we want, I can't tell you how many times people tell me there must be life out there. Don't you believe? And whether I believe it or not doesn't matter. It's the fact that there isn't any yet that we know of. So we have to keep our scientific view there, honestly. I do believe there's probably life, but it doesn't mean it's there. It just means that there's probability it could be there. But you can see there's impacts on Mars. Mars is a really cool planet. But as Earth was starting with life about 3.5 billion years ago, Mars was dying. It lost its magnetic field. And I actually have a sketch of that. Our magnetic field keeps our atmosphere, holds on to our atmosphere, and keeps us from being bombarded by solar wind that strips that atmosphere away. And once you lose your atmosphere, you can forget about having water on the surface and oxygen to breathe. And so that we got to think about what we're going to do with Mars. But the rover here, Perseverance is roving around, this little rover, looking at minerals, picking up some deposits, some soil, and caching it, so sticking it in some kind of container for a future mission to bring back. So that's happening too, and exploring the shoreline, this ancient shoreline. And one thing that's actually really interesting is that there's this helicopter called Ingenuity, which is this little drone. It's the first powered flight on another planet after Earth. So we had, we have planes, of course, and Wright brothers and all of that in the last 100 years or so. Now we have the next, now we have a powered flight on another planet, and that's Ingenuity. This is the first time it's gone on. It goes up about 10 to 30 feet, and it's taken several flights, and it was a last minute addition to this mission to see if the engineers could actually design something that could fly with very little atmosphere, because again, this has not been done before, and it worked. And this is, I like this one. This is an actual picture too on Mars of this little helicopter, which is so interesting. And it's going to be used, a lot of these missions, every mission we send is the next step for the next mission. And we build upon this technology to eventually send people and have really good technology for them to, for the science and for survival. So we're thinking back about Jezero, this definitely had water in the past, and there's no doubt about it. I mean, this is one of many, many examples of ancient river channels on Mars. So it absolutely had water. Now, does that mean it had life? We don't know, but it could. Oh, here it is flying, this little thing. That's a picture too, taken from by the rover. But this is a picture from Shark Bay, and this is in Australia, and these are little mounds called stromatolites. And this is the same kind of mineralogy that we see around Jezero, although it's not living. And it's possible Jezero looked a little bit like this in the past. An analog to this laboratory, as we use these extreme environments on Earth the data sets weren't loaded. And they have this really interesting mineralogy that then we can look for on other planets. And eventually, maybe we'll terraform Mars. We don't know. But this is just showing side by side. This is Earth and its magnetic field. You can see how we know the shape of the magnetic field, and you can see how it holds back the solar wind here. And Mars, unfortunately, doesn't have that. And the solar wind just blasts the atmosphere away. And so Mars lost a lot of its atmosphere. That's basically the reason. So Mars is going to be terraformed. Got to have enough oxygen. It's a very so the first humans to go will likely close. And eventually, maybe, I like this kind of fanciful picture. It's not an actual picture unless they brought a spacesuit to the beach on Earth, but this is just to say that eventually maybe we'll get to Mars and have and it'll be a lot like Earth. Okay, so in the time remaining, what I was going to do is go to, when we talk about habitable zones and exoplanets, and what I'm going to do is turn on, let me see here, hold on a second. Yeah, I'll skip TRAPPIST, but I'll go to, I'm going to go to WASP. So the reason I'm picking these, WASP 96b, oh, WASP 96, WASP. These two systems that I'm going to take you to, they, there's new data from Webb, which is pretty cool. So that's why I wanted to show them. All right. All right. And then with OpenSpace, we can travel faster than the speed of light, which is always fun. And let's go to WASP 96. And so with these exoplanets data sets, what you'll see is the habitable zone. There's all of these exoplanetary systems loaded into the software. And what you'll see is the habitable zone around the star. And they're all different. And so the habitable zone, we have one in our solar system. And if it was our solar system, we'd have the sun and we would be in the habitable zone, this nice green green circle, basically, where liquid water can exist on the surface. And just beyond the habitable zone on this side would be Mars, or slightly on the edge, because liquid water can come up to the surface for very brief periods of time. And on the inner part of the system would be Venus. And definitely with past the habitable zone. Venus is a whole other habitability a long time ago as well, because of its runaway greenhouse. So we're thinking about, and certainly for environmental concerns, you look at Venus to say, oh, what happened there? It's a runaway greenhouse that lost its oceans, and the atmosphere became extremely hot because of all the carbon that went into the atmosphere, because there was no plate tectonics anymore. So it's a whole story of what could happen to Earth if we don't keep it under control. But anyway, this is actually WASP 96. And WASP 96 is a hot Jupiter. So this is the planet. So this is the habitable zone. So we don't have planets in the habitable zone of this system. But this star, and this, these are biosignatures. I'll just skip that. But what was noticed around 96b, this was recent, from Webb, is water in the atmosphere. So the Webb telescope is able to use its excellent instruments to look at exoplanetary atmospheres and say, okay, what can we see in these atmospheres? The data are much better than any other telescope for looking at these atmospheres. And eventually we want to understand what is the composition that means there's life there. And we don't have that answer. We have to suggest that there are certain compositions of different molecules that we can think about for habitability, but we don't actually know. But we do know there's water in this atmosphere, and there's water everywhere in space, but we don't have really great data. This is actually really good data of water around this system. But is this a habitable planet? Not likely. It's sitting right up against its star, and it's a big puffball So it isn't likely that it has life. However, it is a test, really good data on atmospheres of exoplanets. Go to is WASP 39. And this also, the reason I'm going is we'll fly over there. These aren't very far. These are in our neighborhood, yet we could never get there because we don't have technology yet to fly anywhere far at all. So even our closest neighbor, Proxima Centauri, which we're not going to fly to, that has some planets that would take us 70,000 years to get there. So we can just think of that way beyond, way within the habitable zone. But what was cool, this was the other day, carbon dioxide for the first time. And you could see if you look closely in some of these, if you go to these articles and they're publicized in newspapers and stuff, and they'll eventually take you to the data. The little bars, the little lines that go up and down from each dot, those are the error bars. So that's uncertainty. And if the smaller, you can see how good actually the data are, because the little lines too are so are really very small compared to what you'd see from any other telescope. And so this is actually a really nice detection, and for the first time, carbon dioxide. So again, it doesn't mean there's life there. It doesn't mean that you can really deduce that much about it, but it does show we can get the data. And so if we then work with models of biosignatures, trying to like figure out, you know, what is out there, that telescope that'll be launched at some point to then really observe them and say, okay, this is the combination that we see in these planets, and then that planet could have life, and then we can explore that planet. All right, so I'm running pretty much out of time, I think, but I'll just say that in connection to these exoplanets, and what I'll do quickly is just turn on the exoplanets so you can get a sense, because I didn't do that yet, and I don't do that. And so these are, we'll leave, and we'll go back. We're actually going to focus, let's focus back on Earth. And these are the exoplanets. So these are not far. This is our neighborhood. This is like your neighborhood. We're in the suburbs of the galaxy. This is our suburban neighborhood. It's really not very far. But again, we can't go to any of them physically. We have no technology. We have chemical rockets. We've got to work harder if we want to get farther. And other, he definitely did a great job with search for extraterrestrial intelligence, was an active astronomer and really interested in SETI. And so on this Voyager mission, this is a little schematic, he did two things that were really cool. Well, a lot of things, but these two I'll stop with, is that he turned Voyager around and he looked back at Earth. And it was the very first time that anyone saw Earth in this way, as a pixel, which is this little dot, in a sunbeam, which is this band here. And it inspired his essay called Pale Blue Dot. And I encourage anyone who's not, you can Google it. It is really profound. I use it for my classes for astrobiology to give a sense of what that meant. He talks about how we treat our planet, how we treat each other. There's no one coming to save us from ourselves. And when you look at Earth like this, it puts in perspective the impact of what we do to this planet. There's nowhere else to go. This is us floating in space as a little dot. And it was the very first time anyone saw Earth this way, and really arguably, you know, got people thinking about in a lot of ways because of this. And then just looking even farther, this is the golden record. And this is this is a front and back, and there are two of them, one on each probe that's out there. And now they're the farthest we've ever sent anything to space. They're headed out to interstellar space, and there's directions for some extraterrestrials to play it. And this may seem nutty to some people, but remember, Carl Sagan did this and convinced NASA to put this on here with sights and sounds of Earth to make sure that we had a record. We were out there in the universe, that we existed. And he would say, we're not going to be here if they're ever found. It'll be so far in the future, if at all. And so just thinking about, you know, we're not here forever. And if we really want to protect the planet, we have to think about how to do that. And also, if we want to know if we're alone or not in the universe, we have to work harder on technology to try to figure that out. All right, so I'll stop and take any questions from everyone. Thank you so much for listening.
And thank you, Rachel.
Okay, you're welcome. Should I stop sharing? I don't know what I can't see any controls because here I can, what do you want me to do? Do you want me to stop sharing or just leave it up?
Yeah, we'll stop the share.
All right.
And now we'll take questions. So folks, and see what you folks are thinking. But Rachel, I've got a question for you.
All right.
Started. I'm very curious about the way that our space telescopes like Webb collect data, and then how astrophysicists turn it into the gases and the molecules.
Yeah, that's a great question, and actually, I think it's an excellent question, and it's really important to make sure that I think that the information is delivered correctly, because I think what I first saw we've been looking, first of all, we've been looking back in time. All light is looking back in time. I'm looking at you back in time. It's just that we're so close together that it seems instantaneous. But anything farther away really becomes remarkable in that we are always looking back in time with astronomy and astrophysics. And then when you talk about really far back, we've been doing that to do that. But it is important because light travels at a certain speed, at a finite speed. So that's the first thing. So we have been doing that. Now, what astronomers have to do, and there's a great article actually, the New York Times had an article. It wasn't initially published. It was a little unfortunate, I thought, that it wasn't initially emphasized how these images were made, because I think that sometimes the public understanding is that space is so gorgeous and you go out there and it's clouds of rainbows. That is not at all in fact, you wouldn't probably see much of anything because in our sky, but you wouldn't see these beautiful, it's beautiful. I don't want to say beautiful, that's subjective, but you wouldn't see red and blue and green and all these things. So what they do is they take, and I won't go into exactly, there are technical articles on this, which are really good, and they're publicly accessible. You Google them, but they essentially take the wavelengths in the infrared and they shift it to the optical. And so it's very high resolution. So be shifted so we can see it, and then they assign colors, and you have to be told how the assignments are made. So they say, okay, at 4 microns in this wavelength or whatever, this is going to be red, and 2 microns is going to be blue. I'm just making this. 3 microns is going to be green, and then it's all real data, but it's not red, blue, green like you go out with your eyes to see, but it makes it visible. But it's not. So in a way, at least when I tell my students about colorization and false color, which sounds fake, and it, depending on how you think about it, it's always disappointing to me. It's not a universe full of rainbows, but it is all real data, and Webb is getting higher resolution and spectacular view of, you stopped the share, right? So I'm not sharing anymore. Yeah, correct. No, but that image of Carina that I showed, it's all these cliffs, they call it, like these beautiful cliffs and yada yada. It's all there, but you wouldn't see it with our eyes. So it's essentially just shifting it and assigning these colors. And to get more technical, there are articles a lot about this now with Webb of explaining what that is. So it is maybe a little disappointing, but again, good question.
All right, one of the first questions that was if Earth were, okay, here's what they wrote. If Earth were located at the 100 light year radius, would we be able to detect the signals we have sent with the equipment we have?
Oh, that's a great question. Yeah, so the energy does weaken or dissipate as the radius squared. So would we, wait a second. Yeah, I would say, I've never been asked this, but yes, I would say for sure we would be, because we have telescopes that can detect radiation from very far away. So 100 light years is nothing. So if we're out there with some of our detectors, we certainly should be able to see the broadcasts from the early, early TV. Exactly how that would work, I'm not an engineer, but we certainly have the technology to detect it because we're doing that now farther out in the universe. So yeah. So Mars lost its magnetic field, and exactly why it did, we're not 100%. We don't know what happened. But planets have a magnetic field because they have a metallic core and they spin, and that creates a magnetic field around it, like an electromagnet. Something happened with Mars that it was smaller, slightly smaller than Earth. It cooled, it solidified, it lost its magnetic field for all intents and purposes. Without that magnetic field, and have this force is essential for our habitability. It protects us from the solar wind, from these high energy radiation coming in and stripping off. It's like being bombarded with lasers, as an analogy. And so without the magnetic field, the solar wind could then penetrate the atmosphere and kick off. It's called solar wind stripping, strips off the molecules until it's a very thin. There's some still there, but it's very thin compared to what it once was with the magnetic field, and so habitable. So that's essentially what happened: is it lost its atmosphere without a magnetic. If we wanted to make how do you make a magnetic field? I mean, you need like Dr. Evil or something to help you figure that out. I don't know.
Yeah. How do you make a magnetic field?
Nobody knows how to do this. Their ideas are there, but the technology isn't there yet.
Right. Here, real quick. I was thinking about the specific research saying it astrochemistry.
Yeah.
Or it's kind of all the same thing, because you're talking about molecules and carbon monoxide and dioxide and.
Right. It's just sort of jargon at this point. So everyone doing astronomy today is actually really an astrophysicist, and that encompasses, in terms of the definitions, it really encompasses astrochemistry too. You could say technically I'm an astrochemist because I study chemistry up in space. Astronomy really traditionally is about looking. So Galileo was an astronomer. We use that term now kind of colloquially for people, but really working astronomers are astrophysicists, and then some are astrochemists as well. So it's really part of that whole discipline.
So someone interested in getting into the world of studying space, I mean, do they need to know the physics? They need to know the chemistry? They need to know the geology of planets? It seems like
specialized in little, eventually, and this is true for science really in general, is that when you were working scientists, you specialize in something pretty specific. And so, and this becomes very apparent when you go to conferences and people are talking about their specific thing. They have to have an introduction on what they're doing and what they're talking about. And so, geology, I mean, it's a good, it has a lot of regular Earth geology. In fact, I was talking to a former student came by the lab yesterday to talk to us about careers, and it was sort of like a lot of students want to know, what do I have to study exactly to do this next thing? And the answer is you don't have to necessarily study that specific thing, because science translates over. You need to get a degree and some kind of, a PhD helps you prepare to how to be a researcher. But there are plenty of geologists and geophysicists who study and then can easily translate their understanding of that to planetary geology, for sure. And that's where it's really interesting. I actually really love comparing the astrophysics to geology and the connection with meteorites, because it's all, that is the answer, is that if we can study stars forming today and compare to our meteorites, that's geology and astrophysics connecting to help answer some big questions about our existence, So yeah, it can be specialized, and you certainly can translate over from other studies.
Excellent stuff. Well, Dr. Smith, Thanks for being with us today.
Oh, thank you. I hope I answered everything.
Yeah, it looks great. This was fabulous, as
Thank
always.
you, Chris. Oh, thank you. Thank you, everybody. And sorry about Earth. We apologize. It happens. Data is non-predictable sometimes. So, you know, it is. But we're here. We can go outside. And I encourage everyone, please fill out the survey that you get. You try out OpenSpace. It's got great data sets, and we're excited about it. And so we appreciate you looking at it. And I hope it was fun. So thank you.
I did drop the link to the survey in the chat and the comments on Facebook. So yes, if you watch, go ahead, give it a click. It's just a few questions. It won't take you very long, and it'll be great feedback.
Thank you, everyone.
Oh yeah.
Yeah.
So,
got all those crumbs on your keyboards.
Folks, we'll be back here again next week for another edition of the Lunchtime Discovery Series. Make sure that you follow the Museum of Natural Sciences on social media. We're at Natural Sciences, and the Office of Environmental Education, which is at North Carolina EE, to get updates about this program and many more. And I believe you can follow the OpenSpace project on social media, and Dr. Rachel Smith is on the social media as well, often sharing research and work related to what's going on there. Rachel, where could folks
So Astro_Rachel is Twitter, and I occasionally have stuff there of space and goats and donkeys, if that's your thing. Space Donkey 3, it's like 3 donkeys, and I do Space Donkey 3, number 3. And then Facebook, Carolina Museum. I'm there with a donkey. Can't miss it. So yeah, I hope that's so thank you if you want to.
Sounds good.
Follow me there.
Everybody, take care. Stay safe out there. We'll see you again soon.
Thanks,
Bye,
everyone. Bye. Are we off?